Earth, a 4.5 billion year old planet, still evolving. As continents shift and clash, volcanoes erupt, glaciers grow and recede, the Earth's crust is carved in numerous and fascinating ways, leaving a trail of geological mysteries behind. In this episode, the Great Lakes of North America, the largest expanse of fresh water on the planet, are investigated. They hold 20% of the world's fresh water and provide drinking water for nearly 10% of Americans. These 5 lakes are among the world's greatest natural wonders, but their origins are a mystery. Now geologists are investigating, piecing together the clues that lie hidden in this extraordinary landscape. Delving deep into a vast underground salt mine, behind the torrential flow of Niagara Falls, climbing a mile-high glacier, where clues to understanding the Great Lakes formation also provides a window into the formation of the Earth itself. The 5 Great Lakes, Superior, Michigan, Huron, and Erie, pour over one of the world's great waterfalls, Niagara, into Lake Ontario. The mighty torrent of the falls empties excess water from 4 of the 5 Great Lakes out to the sea. For geologists, the lakes are a natural wonder and a puzzle. And scientists are on the trail of how they were formed, with rocks as their clues, and ice, lava, and water as their suspects. Their investigation begins at these seemingly ordinary industrial buildings beside Lake Huron. Hundreds of feet below ground here, there's a remarkable secret. Deep below Lake Huron and also Lake Michigan are vast salt mines carved out directly beneath freshwater lakes.
Right now we're 1,750 feet below the surface of the Earth. We're in the largest underground salt mine in the world, and we're below Lake Huron, a large freshwater lake.
Amazingly, this salt deposit was uncovered by accident.
They were drilling for oil and they hit salt, and that was the end of looking for oil. They just kept on digging for the salt.
This salt deposit is the investigators' first clue. Evidence that there was once an ancient sea here.
Many years ago, the salt was formed in a great salt lake, and the evaporation dry seasons, the salt dropped out, evaporated out, and formed the salt that we're actually mining in.
There are hundreds of layers of salt, leading investigators to conclude the sea must have dried up and refilled hundreds of times. Scientists would later prove this sea finally evaporated millions of years ago. 35% of North America's salt comes from these mines. Salt used to melt ice on frozen roads and sidewalks. Salt used to season food. The remains of million-year-old seas, all coming from beneath Lake Huron and Lake Michigan.
The salt deposit is massive. There's probably trillions of tons of salt in the deposit. It extends all the way down to Detroit. All of Lake Huron, the salt is under it, and all of Michigan.
The salt is soft, and over millions of years the salt layers should have worn away. Why haven't they? It's because the salt is protected by a vast, impenetrable layer of rock that lies like a giant basin beneath Lakes Michigan and Huron and stretches under Lake Erie. Like the porcelain lining a bathtub, the rocky basin holds the lake's fresh water. Geologist John Zawiski and a team of divers are hunting for clues to the Rocky Basin's origins. They're heading for Thunder Bay, a small island at the edge of Lake Huron. As he walked along the beach, Zawiski discovered some crucial evidence, seemingly insignificant rocks that were overlooked for decades. But Zawiski suddenly realized what he was looking at: fossilized remains of ancient sea creatures.
I was seeing something that many geologists had never seen when they visited this island. There were the heads of giant lime-secreting sponges that were some of the main reef builders.
Zawiski uncovered a perfectly preserved fossil of a giant sea sponge that must have come from an ancient coral reef. For the past 5 years, Zawiski's divers have been surveying the lake to discover the size of the ancient coral reef. They believe it's hundreds of feet thick and extends deep below Lake Huron. And Zawiski has proof these rocks are extremely old.
The time period can be pretty confidently bracketed at right around 385 million years ago.
America was then a very different place. 385 million years ago, its landmass lay in the southern hemisphere, a land covered by ancient warm coral seas.
This region was just south of the equator in tropical conditions, and shallow seas had swamped many of the land areas of the Earth at that time.
Year in, year out, coral reefs decay naturally and turn into a soft rock, limestone. And much of the rock Zawiski's divers find under Thunder Bay Island consists of layer upon layer of this limestone from successive coral reefs. But millions of years ago, some of this soft limestone near the surface was changed. When the salty, briny sea evaporated, it turned the limestone into a second, much harder rock, something which would decide the very shape of the Great Lakes.
This rock is limestone. This other piece was once the exact same material. However, it's been converted by a process of brines, creating the conditions for recrystallization into a rock that we call dolostone. It's much harder than limestone, more weathering resistant, and I can easily demonstrate the difference between these two: calcium carbonate, calcium magnesium carbonate.
To show the relative hardness of the two rocks, Zawiski uses an essential tool in the geologist's arsenal.
Let me put a little acid on here.
Acid easily attacks and dissolves soft rocks. First, how will the limestone react?
You can see a very violent reaction there. Carbon dioxide gas is being released from the limestone.
Next, the hard dolostone.
Let's go ahead and do the acid test on it. And you can see we don't get this violent reaction, almost no reaction at all.
Zawiski has proved the dolostone layer is harder and more resistant than the limestone. The ancient ocean's salty water converted the top layer of the limestone deposit into a cap of hard, resistant dolostone rock. It's this that forms the super tough rock basin under 3 of the 5 lakes: Michigan, Huron, and Erie. Scientists were beginning to piece together the chain of events that led to the formation of the Great Lakes. The clues uncovered so far: vast salt deposits provide evidence of an ancient ocean. The briny ocean changed soft fossilized limestone into hard dolostone. Dolostone makes up the rocky basin under lakes Michigan, Huron, and Erie. The tip of the rock basin, the rim, forms steep cliffs that tower above these 3 lakes. This immense wall of rock, called the Niagara Escarpment, forms the boundaries of these lakes and makes possible one of the world's greatest natural spectacles, Niagara Falls. Over this hard dolostone cliff 3,000 tons of water a second tumble from 4 of the 5 lakes. But it's more than just a miracle of nature. Niagara Falls is a vital clue that helps scientists date when fresh water first began flowing into what we now call the Great Lakes. The Great Lakes of North America. Geologists have discovered 3 of the lakes were formed in a vast rock-lined basin laid down by an ancient lagoon. The question is when? And they think the answer lies here, Niagara Falls. Behind this curtain of water lies the evidence to when the lakes were made. Like the overflow from a bathtub, excess water from 4 of the 5 lakes, Superior, Michigan, Huron, and Erie, spills over the falls into Lake Ontario. And all that water is changing the falls, change that can be measured and used to calculate the age of the lakes themselves. The falls were first studied by one of modern geology's founding fathers, Charles Lyell. Lyell, who'd pioneered the early understanding of Earth's secrets, was intrigued by the concept of geological time.
Charles Lyell came to Niagara region in the 1840s, and he made very important observations at Niagara Falls. Lyell was using the principle that things that we see going on today can be used as examples for what went on in the past.
Lyell believed the world wasn't shaped in a few days or even years, but by slow change over millions and billions of years. This directly contradicted the much shorter time biblical scholars said the world had been in existence. Lyell realized that dramatic geological change was going on in front of his eyes at Niagara Falls. If he could measure it, he might be able to calculate the fall's age. Lyell's technique was brilliantly simple. He noticed below the falls was a great gorge, which locals said was steadily increasing in length as the water wore away the ledge of the falls. The falls, they said, were moving slowly upstream. Head to the base of the falls and you can see why. The cliff face is being worn away. The falls are formed by a cliff capped with a ledge of the same hard dolostone rock created, as we've seen, by seawater. Beneath the tough dolostone cap is a layer of much softer rock called shale.
As the water crashes over the dolostone, it erodes out these soft shales that are underlying the dolostone, and the blocks can fall down from the face. On the right, then, you can see these massive blocks of dolostone that have fallen down at the bottom of the waterfall.
Each time the dolostone ledge collapses, the falls move further upstream. Lyell believed this process had been going on for thousands of years and was still continuing. It had begun as the lakes were first formed when water began wearing away the hard dolostone ledge of the falls. To discover the age of the falls, all Charles Lyell needed was some simple math.
He realized that the falls had started at the Niagara Escarpment, which is about 35,000 feet from here. So if the falls receded at 1 foot per year and receded 35,000 feet, that would give an age for their present position of 35,000 years.
Lyell's calculation was based on simple measurements, but wrong guesswork. He thought the falls were receding by 1 foot a year. But today, we have much better records to go on.
This plaque commemorates Table Rock, which is where the falls were in the beginning of the 19th century. Since that time, they've receded about 600 feet to my right.
So in the last 200 years, the falls have steadily retreated at a rate of not 1 foot, but an astonishing 3 feet a year. So instead of Lyell's calculation of 35,000 years old, The Niagara Falls were a third of that figure, just 12,000 years old, a mere blink of an eye in Earth's 4.5 billion year history. In the search to find what created the Great Lakes, scientists now had a crucial clue: the age of one of their key features. Born at the same time, the falls is the overflow for all the upper lakes into Lake Ontario and the sea. So if the falls have only been around for 12,000 years, then it means the lakes themselves must also be incredibly young. Now that scientists had worked out when the lakes were created, the next question was, how? What immense force could have created not one, but 5 huge lakes? A force so powerful it must have left a trail of incriminating evidence across the region. Geologist John Menzies scans the landscape to track the mysterious force that created the Great Lakes. And he's spotted something unusual: strange teardrop-shaped hills, one after another, called drumlins.
Some are small, fat, and streamlined. Some are extremely elongated. This one is about almost a mile in length, 150 feet high, and about 200 feet across.
This is the evidence that John Menzies has been looking for.
There are many drumlin fields in North America, but this one is a particularly large field. It has anywhere between 60 and 80,000. So it is truly an enormous drumlin field.
Each drumlin points in the same direction, north, to where an immense force came from. This tells Menzies they were all created by the same powerful object. But what was it? The answer lies 4,000 miles away, high in the Swiss Alps. Here, the culprit is plain to see: snow and ice. Switzerland is home to some of Europe's largest glaciers. They're giant rivers of ice that flow down mountain valleys. Glaciologist Dr. Andreas Bauder studies how glaciers can transform the landscape. What he discovers here could also point to how the Great Lakes were made.
We measure the movement of the ice. This reflector reflects a laser signal coming from a theodolite, giving us the position of this stake, and so then we can calculate the movement. My colleagues down here are drilling deep holes down to the base of the glacier to install instruments to understand how the glacier is changing here.
Bauder's measurements reveal this glacier moves over 10 feet every month. Here, a seemingly stationary glacier is shown moving down the mountain, recorded by time-lapse photography over a year. To find out what's driving it, Bauder climbs high up the glacier. This glacier is thousands of years old and almost a mile thick in some places. Ice that's a mile thick weighs a colossal 3.8 billion tons per square mile. That's the weight of 59,000 fully laden supertankers. And it's this immense weight that makes the glacier such a force to be reckoned with. Its weight is slowly pushing the glacier down the valley, gathering anything in its path, collecting rocks and debris. The rocks act like the blades of a giant bulldozer, scouring the ground, digging up yet more and more rock and soil. But when the temperatures rise, the glacier melts, retreating up the valley and leaving rocks and debris behind in huge piles. This is how the teardrop-shaped drumlins back in North America were formed. They were bulldozed, landscaped by a powerful glacier. A glacier that may also have gouged out the Great Lakes. The evidence is coming together. Niagara Falls, dated just 12,000 years old. This suggests the lakes themselves are very young. The presence of thousands of drumlins pointing to ice that carved out the Great Lakes. It's a convincing case, but there's one problem. The Great Lakes cover an area 5 times the size of Switzerland. No glacier that size has ever been known to exist. Geologists were on the hunt for something even more powerful that could have created such huge destruction. A kind of prehistoric monster roaming over North America. Geologists are scouring the landscape, searching for evidence of a massive force. One that was capable of gouging out 12 trillion tons of solid rock, enough to create the Great Lakes of North America. It would be a body of ice so large that it would break every record, defy all logic. Geologist John Menzies hunts for evidence of this prehistoric monster just south of Niagara Falls.
This whole area was covered by the ice with a tremendous torrent of sediment and water between the ice and this bedrock. And as the sediment moved across, it produced these superb striations and parallel scratches and marks.
And there's another clue. Giant boulders of hard crystalline rock called granite. These hard, massive rocks sit in a flat, sandy landscape. They shouldn't be here.
This is what we refer to as an erratic boulder. It's granite. It weighs some 80 to 100 tons. It would actually be frozen up into the base of the ice and then moved kind of like a conveyor belt along on the base of the ice down to this part of southern Ontario, some 400 or 500 miles to the south from the Canadian Shield, where with ice retreat and the eventual melting of the ice, this boulder's been left to sit as we see it today.
Erratic boulders moved hundreds of miles from northern Canada, scratches on the bedrock, and drumlin hills. The evidence is mounting. There was ice here once, lots of ice. Geologists map these glacial features together, and an extraordinary picture emerges. Not of a glacier, but of a vast ice sheet 1 mile thick and over 2,000 miles long. It stretched all the way from the North Pole as far south as Chicago and New York, leaving a trail of destruction in its path. Here was a force powerful enough to create the Great Lakes. But even this vast sheet of ice couldn't have gouged out basins that are over 1,300 feet deep. It seemed the culprit wasn't working alone. At Scarborough Bluffs, just 100 feet from Lake Ontario, John Menzies has spotted an unusual deposit at the cliff face. Layers of rock provide him with a kind of geological time machine. The deeper he looks, the further back in time he goes.
You could say that this is a journey through the last 60,000 years of geological history in this part of Canada. This lower formation is 65,000 to about 40,000 years ago. The next layer is between 25,000 and 10,000 years ago.
Menzies focuses on the dark layers sandwiched between the light ones.
What we have here is a sequence of sediments which illustrate the movements of the ice front back and forward across this part of Canada.
These dark layers mark the exact end of each ice age, formed of organic material when plants grew again at warmer temperatures. Here, John Menzies has proof that ice ages return twice to this spot during their cycles of destruction. In fact, across the Great Lakes region, geologists have found evidence of up to 10 separate, enormous ice sheets. As each new ice sheet advanced, it carved the Great Lake basins deeper and wider, eventually forming the largest lake system in the world. But the ice left vast areas unscathed. It suggests there was some other force at play, something in the lake's ancient past that set them apart from the surrounding landscape, making them particularly vulnerable to the ice sheet's attack. Menzies decided to dig deeper, down to the landscape that existed before the ice ages. Going back 2.5 million years, he found evidence of a chain of ancient rivers flowing across what's now the Great Lakes region.
The pre-glacial topography of the Great Lakes Basin mirrors the existing Great Lakes system and Great Lakes basins that we see today.
The ancient river's pattern and flow exactly mirrored the shape and position of today's lakes. It's no coincidence. These rivers formed valleys that affected the way the ice sheets moved.
As the ice sheet advanced to the south, it would tend to follow the pre-glacial rivers, and so you get these really fast-moving zones of ice which create a tremendous amount of erosion in these pre-existing depressions.
The ancient river valleys funneled the ice sheets into fast-moving super ice flows. Menzies believes the coarse sediments the rivers left behind dramatically accelerated the ice sheet's flow.
This sediment acts as a kind of lubricant, a bit like ball bearings underneath the ice. It would actually speed it up quite appreciably.
These fast streams of super ice were even more destructive to the landscape. The case is coming together. Drumlins clustered across the landscape testify to the vast ice sheet's brutal power. Dark layers of rock reveal the ice was a serial attacker, while a network of ancient rivers left some areas more vulnerable to these attacks, turning slow, lumbering ice into destructive, fast-moving super ice. These gouged out all the loose rock and sediment down to the hard dolostone layer, the rocky lake floor. The result? The basins of the Great Lakes. Case closed for 3 of the 5 lakes inside the Rocky Basin, but not for the other 2. Lakes Ontario and Superior are outsiders. The theory doesn't fit. They're simply too deep. In an attempt to find out why, a daring underwater expedition would investigate Lake Superior, the largest, deepest, greatest lake of all.
Roger that.
The hunt is on to discover what formed the Great Lakes of North America. Geologists have found compelling evidence that the Central Lakes lie in a vast rock-lined basin, laid down by an ancient lagoon, gouged out by giant ice sheets. But when it comes to Lake Superior, the theory doesn't fit. The greatest of all the lakes at over 1,300 feet deep, it could almost submerge the Empire State Building, and it lies outside the Rocky Basin. Lake Superior isn't just deeper than the other lakes. Its floor is the lowest place on the North American continent. Over half of this mighty lake lies below sea level. The question is why? Canadian geologist Henry Halls was convinced the explanation could be found at the very bottom of the lake.
The opportunity came up to study a very remote part of the lake. It's almost in the geometrical center, and it's called Superior Shoal. And people didn't know what the rocks were there, and they didn't know why it was there.
In the summer of 1987, Halls led an expedition to the lake's dark, unexplored depths.
We went down. It took us about 15 minutes to go down, and it gets completely black, apart from the searchlights of the submersible. And when we reached the bottom, the pilot, he said, "This is very strange." He said, "I'm getting echo sounds coming back," he said, "more or less from all directions."
It does look almost vertical. It is vertical. It's more than vertical. More than vertical, we've heard. In fact, it's hanging over us.
Deep in the center of the lake, on the border between Canada and America, Halls came across a strange rock formation.
The pilot He said, it seems that we're in some sort of a chimney or something like this. He said, I'm not sure what it is.
Halls and his submersible were in a deep canyon 1,200 feet below the surface. Intrigued, he took an even closer look at the canyon walls.
And as we climbed, I started to see striations like this. They were actual glacial striae on the sides of what presumably was a canyon.
We are continuing to move up this vertical face.
Halls had uncovered a vast canyon lined with striations or scratches from the glacier that had carved out the lake. But it was the type of rock that was the clue to Lake Superior's exceptional depth. He used the sub's robotic arms to take rock samples from the canyon walls. The canyon was made of dark basalt rocks. The discovery of this rock took the investigation in a surprising direction. Basalt could only have been formed by intense volcanic activity. Basalt is created when hot magma deep within the earth wells up to the surface. 1 billion years ago, immense forces pulled the Earth's crust apart here, forming a rift valley. Hot magma seeped up through the cracks in the thin crust. As it cooled, it lined the valley with a layer of hard basalt. Then, over millions of years, the rift was filled with soft sedimentary rocks.
So there's a tremendous thickness of infill in that lake lying above those volcanic rocks. And all of this is relatively soft.
Many geologists believe the exact same volcanic action accounts for the formation of the fifth and final lake. Ontario, on average, is the second deepest lake. A separate rift valley appeared here much later than the one under Lake Superior. The volcanic split in the landscape stretched as far as the ocean, creating Lake Ontario and the St. Lawrence Seaway. Millions of years later, the mile-high ice sheet easily carved out the weakened Rift Valley structures under Lake Superior and Lake Ontario. The extraordinary story of how the Great Lakes were made is almost complete. Ice sheets repeatedly carved out soft rock down to the hard basins of the Central Lakes. And to the north, ice attacked billion-year-old rift valleys to make the deepest lake, Lake Superior. The same action was repeated at Lake Ontario. When the ice melted for the last time 14,000 years ago, it filled the lakes with fresh water. It sounds straightforward, but there's a problem. There's so much ice, the Great Lakes should be many times bigger than they are today. Just when geologists thought they'd solved the mystery of how the lakes were formed, a new puzzle emerges. Where did all the water go? Geologist John Menzies is investigating exactly what happened at the end of the last ice age, when a vast ice sheet, 1 mile thick and stretching to the North Pole, started to melt. He believes it was so large it should have created far bigger lakes than the ones we see today. He's looking for evidence of one of these prehistoric lakes. As the ice sheet melted, a vast freshwater lake appeared that geologists call Iroquois. Then, later, as Lake Iroquois dried up, it left beaches which can still be seen today. Menzies believes he can detect these ancient beaches in the gently sloping landscape surrounding Lake Ontario. As Menzies drives uphill, away from the present-day lake, he's traveling back in time across Lake Iroquois' ancient shores.
We're crossing one shoreline after another. The reason we know they're shorelines is that they contain large zones of sand, beach sands and beach bars and spits. The oldest being about 12,000 years ago, the bottom shoreline being about 6,000 years ago.
Getting to the top of the hill, 400 feet above the level of today's Lake Ontario, Menzies is standing on the ancient shore of the original lake.
The present-day Lake Ontario is off there in the mist, and we're sitting about 400 feet plus on this beach, which was formed maybe 10,000, 11,000 years ago, and then the ultimate oldest beach is about 12,000 years ago.
These ancient beaches, now buried under the surrounding landscape, are evidence of a colossal freshwater lake.
We're looking at a vast amount of water. When you think of the water, it's stretched from here to beyond the present lake, way into New York State, beyond into Rochester, so it's a huge, enormous inland sea.
Despite their size, the Great Lakes today are just a small fraction of these vast prehistoric lakes. The water has vanished. Geologists want to know how they emptied. 50 miles east of Toronto, at India River Canyon, Menzies picks up the trail of the missing water torrents.
Okay, what we have here is an enormous subglacial pothole formed by subglacial meltwater exiting underneath the ice sheet, typically formed with a large roller ball which rolls around in these really torrential vortices. The meltwater is chock full of boulders and sediments, and in this instance it's drilled itself the whole way through.
These potholes are evidence of a catastrophic flood, of huge volumes of water moving at high speed. This flood needed an escape route, and Menzies believes he's found the place.
This would be an enormous torrent, possibly at least a couple of miles across, and could easily have been 200, 300, 400 feet deep, moving at an incredible velocity.
Nearby, a steep gorge, yet more evidence of the floodwater's terrifying power. The stream that remains today couldn't have cut such a huge amount of rock.
And what we've got left is what we call a misfit stream, which is the fairly small Indian River, and this, if you like, is the remnant of that enormous torrential flood.
Geologists believe as the ice sheet retreated, it uncovered this ancient India River outlet, allowing vast amounts of meltwater to tear down towards the sea. Finally, 12,000 years ago, the ice retreated, freeing the St. Lawrence Seaway and allowing the lakes to settle into their present flow. The story of the Great Lakes is coming together. Ice sheets repeatedly ground out deep basins, digging out ancient weaknesses in the Earth's crust. Prehistoric beaches show that when the final ice sheet melted, the water flooded the basin to create vast superlakes like Iroquois. And as the ice finally retreated 12,000 years ago, the excess water drained away to leave the Great Lakes we know today. But even now, as we know how the Great Lakes were formed, they are still changing. And scientists predict one day the lakes might disappear forever. The Great Lakes evolved over 1 billion years. Today, they're a vital link between the cities bordering the lakes and the sea. They provide over 20 million people with drinking water and irrigate crops throughout the Midwest. But in the past few years, fears have grown about the Great Lakes' future. Water levels are falling. People who have worked the lakes for years believe they can already see a change.
We noticed a drastic decrease in water levels right after the September long weekend, where the water in a week dropped a foot, and throughout the remaining of the fall it went down about another 2 feet. And you can notice that by the pinker or the brighter colored rock versus the rock that's typically exposed to the weather. And what we saw there was a clear example of how the water has dropped a good 3 to 4 feet.
Many have been quick to blame global warming for the fall in lake levels. But geologists believe there is another force at work. The ice sheet that cut out the lakes was so heavy, it pushed down on the Earth's crust. Now the ice sheet has gone, the crust is bouncing back. Incredibly, 9,000 years since the end of the last ice age, the ground is still lifting. In the north, where the ice was thickest, land has risen by as much as 1,800 feet since the ice melted away. Toronto's famous CN Tower appears to be getting higher. As the crust bounces back, the land it's built on beside Lake Ontario rises nearly an inch each year.
The CN Tower is part of the landmass here, so in fact it's rising out of the land. In fact, the whole land surface is rising slowly.
Lake Nipissing today is a small body of water to the north of Lake Huron. 12,000 years ago, when the ice began to melt and Lake Nipissing first formed, it lay at sea level.
Lake Nipissing, an enormous lake there. Again, as the land rebounded, so the lake eventually drained out and the land rose slowly, so the land is now 400, 450 feet above sea level.
Geologists call this crustal rebound, and it dramatically affects the delicate balance of the network of small rivers that feed the lakes.
This is an interesting example. If we think of trying to explain crustal rebound, and we look at this river as it flows out into the lake at the moment, if we have crustal rebound, the land comes back up, this river in fact will cease flowing out into this lake.
It's this crustal rebound that's partly responsible for the fall in level of the lakes. And as the lakes empty, their weight decreases, allowing the crust to bounce up even faster.
Lake levels will fall, so the amount of water in the basin will in fact become less, and the effect of that will increase the rate of crustal rebound. The land will come up even faster than it's already doing and continues to do.
As the crust rises, the lakes slowly empty. But in a few thousand years, the lakes will face another, even more dramatic change.
One of the exciting things about geology these days is not only looking at the past, but is looking into the future. In other words, having the ability to start to predict what might happen in the next several millennia.
And the future is here at Niagara Falls, at least in geological terms. Every year, the falls are retreating 3 feet upriver. Only 12 miles and 21,000 years to go before they're back into Lake Erie. When that happens, everything will change, and fast.
If the falls eroded all the way back to Lake Erie, which would take some thousands of years, the levels of all the upper Great Lakes, Huron, Superior, and Michigan, would adjust to the lowered level of Lake Erie by dropping as well.
The land between the falls and the lakes acts as a block. It's the Niagara Escarpment topped with hard dolostone rock. When the falls cuts its way through this rock, the water levels in all the lakes to the west would drop by a staggering 180 feet, the height of Niagara Falls. Almost all of Lake Erie would drain away. One day the lakes may disappear altogether. But geologists also predict a new cycle of ice ages will begin again.
So an ice age would begin, and this ice age would then cover, we would expect, at least 30% of the land surface as it did in the previous ice ages.
And when the ice returns, the lake basins will be cut even deeper before filling again with water. The largest freshwater lake system in the world has had an extraordinary past. A basalt-lined canyon discovered at the bottom of Lake Superior shows that 2 great rifts opened up below Lakes Superior and Ontario. Fossilized sea sponges are evidence of an ancient briny sea that laid down the rocky bowl that holds Lakes Michigan, Erie, and Huron. Thousands of drumlin hills are proof that vast ice sheets repeatedly scoured out the lake basins. Born just 12,000 years ago, the Great Lakes as we know them today are just a transient feature. They've only existed for the geological blink of an eye. But their story hasn't ended yet. The Great Lakes are changing and evolving, an endless process like the Earth itself.